So first of all, let me thank the organizer. Michał is gone, but Johannes is still there, here, and also the local teams, Carpe, Martina, and the rest that they have done really a wonderful job to get us here together. And they have done also a very nice work organizing the people, because we have a Danish session and we are having a Spanish one without you realizing, because we started at 10 a.m. here in Barcelona, and we have made a trip to the south, where Polytechnic of Madrid is. They changed my affiliation, but I didn't mind, actually. They said I'm Polytechnic of Madrid, but I am here in the south, in Granada. That's where the University of Granada is. And be prepared, because we are leaving Spain to go even south after me. And Sadiq will go all the way down after me. So my talk is going to divide in two kind of Rydberg molecules. I'm going to talk first about one Rydberg molecule, which is formed with a Rydberg atom and a diatomic molecule. And the second kind of Rydberg molecule I'm going to talk is about two diatomic molecules, one in a Rydberg state, forming a larger Rydberg molecule. So I wanted to make an intro. I thought it was not the point to make an introduction of what a Rydberg atom and why Rydberg atom is so Rydberg physics is so important, because we had already several talks about Rydberg, like from Tillman, Florian, Valentina, Johannes, which I think is gone. No, he's there. Sorry, Johannes. You were always here. So, sorry. But so I decided to go directly to the center of the talk, which is what are Rydberg molecules. And here we have three examples that they have always been in literature. So we have a Rydberg state of molecule. We just have an example here is a diatomic molecule with one of their electrons in one of a highly excited orbit. We also have this heavy Rydberg state of molecules, which consists of vibrationally excited molecules. And the point there is like the energy levels of this vibrationally excited molecule, it approached a kind of Rydberg-like series. And then we have this one, which was Robin Cotte was working actually on that one, and many other people, where we have two Rydberg atoms, and they form these microdimers, where we have a Rydberg atom with another Rydberg atom. But the list is longer. There was this first, was in 2000 when Chris Green and Hussein Sakdepur proposed theoretically the Rydberg atom interacting with another ground state atom, and they will form this ultra-long-range Rydberg molecule. Here what we have is like the ground state atom locally prove the wave function of the Rydberg electron, and we get this kind of oscillating potential where the important point is like the abound state where the huge molecule could exist. They were seen already quite a few years ago, like 13 years ago, in the group of Tillman-Fau, and they have been described with the electron-atom scattering. This electron is like the interaction is described with the electron-atom interaction with this Fermi pseudopotential, where we have here the interaction with the S-wave scattering length and with the P-wave scattering length, and they have seen in many systems. In this conference, we had already like 3 talks where they were talking about this new type of long-range ion Rydberg atom molecule. This is one of the pictures from Tillman-Fau's group, and it was first proposed by a group of Georg Reitel and Johannes Heggendessler here. And then we have here, this is an ion here interacting with a Rydberg atom, and then we have another kind of Rydberg molecule which have been very successfully observed experimentally. The molecules I'm going to talk to you, they are a little bit different in the sense that what we change is the ground state species, what we add to the Rydberg atom. And in that case, what we have here is a Rydberg atom, and now what we put is a diatomic polar molecule. We have a dipole moment, and then what we have in this case is like the binding mechanism now is a little bit different. It's this anisotropic scattering of the Rydberg electron with the dipole moment of the molecule. There was a first theoretical proposal by Seth Rittenhouse and Hussein Sakdepur already 12 years ago. Time is flying, actually. And where they have the Rydberg, I think they have rubidium and as an atom, and for the diatomic molecule, what they did was to assume it could be described as a 2-state system, like a Lambda doublet molecule. And that's where they get here. Here you have the Rydberg core. Here you have the Rydberg molecule, like the diatomic molecule, which could be pointed towards the ion or away from the ion. That will be how the electronic structure look like. And that will be the potential as a function of the internuclear distance. And what they have is this oscillating potential, which is important that they have potential wells, that they are deep enough for this large molecule to exist, where the molecule will be bounded. And due to this Lambda-doublet description, this two-state model for the diatomic molecule description, they have these two types of potential, where they have either to the left or to the right, and this indicate where the dipole moment of the diatomic molecule is pointed away or towards the ionic core, and they have enough space to accommodate the one state. So we came into the game to collaborate with them already a few years ago, and that was the proposal. It was a collaboration that with Seth Rithenhouse, Hussein Saktepur, and Peter Smelche. And what we came to the game was to say, okay, there are many diatomic molecules that they cannot be considered as a two-state system. They have a rotational structure, and these have to be taken into account. So that's what we did. So it's like the same. We have a diatomic molecule here. We have here a Rydberg atom. And if we consider like a diatomic molecule, we could make all the approximation on the way through Bohr-Oppenheimer and then split vibrational and rotational equilibrium and assume that what we can do describe this system is as a rigid rotor. Let's assume that it's not a floppy system and it's a diatomic, well-behaved rigid rotor. Let's say like that one. So when we describe a field-free molecule, what we have is the rotational kinetic energy within this rigid rotor approximation. And then on like on gas phase, we will have the dipole moment of the diatomic molecule pointed in any direction. And then what we have is that the core and the Rydberg electron, it produce an electric field. And that's the electric field produced by that will be the part of the core, and that will be the part of the Rydberg electron. And this diatomic molecule is going to interact with this electric field because it has a dipole moment. And when we have a diatomic molecule in the presence of a DC electric field, we get this effect of the orientation. The diatomic molecule is like now it's not freely rotating any longer. We have the molecular fixed frame is fixed in a space. And on the top of that one, we have a well-defined direction of the dipole moment. That's what is called orientation. And this, it's a little bit exaggerated, the figure, but then the dipole moment is pointed depending on where the electric field is. So what we did was to describe the full system within the Bohr-Oppenheimer approximation. That will be our system here. We have the core here, the Rydberg electron, the diatomic molecule, and the total Hamiltonian describing this system has two parts essentially. That will be the Rydberg electron Hamiltonian, which is given here. And then we have the second part, which is the Hamiltonian of the Rydberg molecule. What we have here, the rotational kinetic energy. And we have, as I said before, the interaction with the dipole moment and the electric field produced either with the core or with the Rydberg electron. Here we have, this is the Fermi telecritical dipole moment that Roland Wester was talking about. If the dipole moment of the diatomic molecule is larger than this limit, the diatomic molecule might capture the electron. And then we will have a core with the diatomic molecule. So we need to to consider diatomic molecule having a dipole moment smaller than this 1.6 or 7 Debye. I am talking as in a different regime, like Johannes and Valentina, they were talking, because for me, the electron is a key player here. The electron is going to make the game, it's like the binding mechanism. This part of the interaction of the electric field is the key one to make the bonding. And well, we solved this for the theoretician that they love. We love all this. We solve this system making a basis set expansion in a couple bases where we have here the electron wave function, and here we have the rotational part of the molecule. That will be the structure, how the potential energy curve look for potassium with KRB. And what we have here, you can see in this side, we have here the diatomic molecule, the Rydberg atom here in different states. And here indicating also the orbital angular momentum. And I have here the diatomic molecule. And what we see is like a dot, as a large distance, they will not interact. So we have just the sum of both energy, the Rydberg electron with diatomic molecule. And then all these lines indicate with the same color, indicate when the diatomic molecule is rotationally excited. So I have n equals 0, 1, 2, 3, 4, 5, until I find with the next Rydberg state. And then we have the blue, and then we have the green one, where we have 43s, and so on. If I zoom it, because these curves look very flat, if I zoom in, that will be a typical how the potential look like when the Rydberg atom is in a 41D state. And that will be one of the states that they can easily excite with these two photon excitation. And in that case, we have rotation. The diatomic molecule is a rotational excite. And this horizontal line are bound state. This is where the molecule will exist. It's narrow, but still they could be seen. Since this state is very isolated, this molecule, this Rydberg molecule, will have a small dipole moment because there is not a strong mixing of this 41D with other electronic states from the Rydberg atom. So if we look here, up here, these are all the states coming from the degenerate manifold. And then there are larger vibrational spacing. There are a lot of curves where they could be formed, this molecule. And the different point here is like this curve, they don't have a large S or D character in terms of the Rydberg wave function. So what we did was, together with Peter, Seth, and Hussein, we engineered a way that the states coming from this upper degenerate manifold, they acquire some S and D character where the experimentalists could easily photo associate. And for that one, what we have here is in horizontal, you have the rotational excitation of KRB. And in this tilted line here, we have the energy splitting of the NS and ND. Actually, they are both with respect to the degenerate manifold. We are both in the same color, and this is done for potassium. And every time these lines cross with the other one, that indicates that I will have KRB in excited state close to where the degenerate manifold is. Let me show you this. So I have to look to this crossing here in order to have KRB in n equal to 2 with the Rydberg atom in one of these close to this excited state. And this is what we have here. We have 58S with KRB. And we see here that this state now is shifted towards all this degenerate manifold where we see is the action happening. And this is all of these terms here, the avoided crossing between one of these states shifted down and the other one shifted down. Now we have a larger vibrational splitting, and we have also a larger dipole moment because there is many partial wave from the Rydberg electron contributing. So that will be good for the experimentalists because they could photo associate here and create this molecule. And as I said, that the weight of the wave function, of this wave function, that's the weight of the Rydberg electron orbital angular momentum. And you see here now the dominant one, or one of the dominant one, is the S character. So how general is that one, and will be created experimentally? So we started to collaborate with the group of Simon Cornish and his postdoc Alexander Guthries. I didn't pronounce it properly. Where they have, they are expert in creating ultracold molecules. So they wanted to do the experiment with either rubidium or either cesium. And actually here I am going to show you already the result with cesium combined with rubidium cesium. We prove our description in order that now we include also the way that the electron is scattering with the rubidium cesium, and we make we include the Fermi pseudopotential with the S wave scattering length between the electron and the rubidium cesium here. And one of the a way that they might create this system is having two optical traps, where here you have the Rydberg atom, and here you have the diatomic molecule. Now the diatomic molecule is like almost 3 Debye the dipole moment, so it's excellent, and 0.5 gigahertz. And for that, when they have these I said optical trap, they're optical twisters, sorry. These two optical twisters, they could go around 0.5 micron, I was told by Simon. So this will be in that regime where we have to create the cesium Rydberg state. The cesium should be in close to n equal to 70. And that's what I'm showing you. I am showing you the structure, the electronic structure of cesium in n equal to 70 with rubidium cesium. And there you have the 74S. And then what we did was to analyze what happened now if we have the rubidium cesium in this ground state, and we have the cesium now coming, and they will come, they will be the entrance channel here, and they have an avoided crossing here. And when we see this avoided crossing, that will be the avoided crossing here, that's the Landau-Zerner probability. And what we see here is that this is the probability, and actually I missed I have the velocities. The velocities that each of these curve is for a different velocity, and the velocities are too high to be ultra cold, so they are very large. That indicates that if they are in the ultra cold regime, with the normal velocity, that will be passed adiabatically, so they will ramp down here and they will be created the molecules here, and that they have many bound state here to create this molecule. This is all the electronic structure here with the bound state. And here we show you, for all this bound state, I'm showing you the contribution of this all partial wave in order to see that they have an S character, because I was entering here in a S character, and you see the S character, which is this point, is really low, and what is dominating is the sum of all the higher partial waves. And if we look to rubidium cesium, what is the mixture? What we have really is, for the rotational structure of rubidium cesium, we have n equal to 0 and n equal to 1 dominating these two states. If they pass this is the dipole moment in atomic units, which is, you see, it's very large, as expected for this Rydberg system. So if they go up here we made a treatment taking into account the coupling between those two states. And if we look to this bound state, which are like stable compared to that one that they will dissociate, we also have a complicated contribution from the L equal to 0 state, which increase as we approach the avoided crossing with the upper curve. And in terms of the rotational state, we have this one there. In case they want to have both here in the same optical twister, they have to go to lower S wave, like N. That will be, we make this calculation for N equal 31. And that will be, I'm going only showing to show part of you for that one. That's how the spectrum look like now. We have 31 L larger than 3, and we have all this. This is actually not no, that will be the correct one. So there were a mistake here with the numbering that we did. So that will be the 35S, 35S1, and so on. And then you see that this is very complicated, highly complicated. If I am coming here through this avoided crossing, that will be the first one we enter. And that's also, again, it's like all the avoided crossing at the speed that they have, it will be crossed adiabatically, so that they have to come down here. And here you have all these states, and then you really see that they all gone through really in a adiabatic way. And here I have, for each of these minima, I have some for the bound state. You see here that all of them are dominated by the highly partial wave, and only the two bound state here, the lowest one, are dominated by this S wave character. So somehow it's dominating all the partial wave coming down from the Rydberg degenerate manifold are dominating this system. And for the rotational spectrum is level. So let me continue, because I'm realizing I only have 7 minutes. 7 minutes left. Let me continue with now the second type of Rydberg molecule, where we have here a Rydberg state of a diatomic molecule, and we have here a diatomic molecule. In that case, we are considering NO in both cases, especially because like Tillman-Fau group is working with this molecule. And we have here the electronic structure of NO, which is highly complicated. And we are going to work in both directions. We are going to, in both parts, we are going to work here in the electronic states. And this is the advantage. This is a Lambda-doublet molecule, like we were told already. And we can describe this molecule only assuming that these last two states with different parity are enough to describe the system. And here you have the splitting and the dipole moment. It's a very small dipole moment, but the splitting is also very small, which will also play in our advantage. And we go to a Rydberg state. The Rydberg state is somewhere here. And the advantage of the Rydberg state, NO, it's been heavily studied. I was really surprised when we started to work with NO, the amount of theoretical study for this molecule. Jonathan Tennyson, he said to me in an email, we did it. He was the one computing that we are using this quantum defect that he computed already in the 90s. And he said to me, we did it because we could do it, not because he thought it could be usable for something. So now we are using them. So we used his quantum defect to produce the electronic wave function of this diatomic molecule. And the description is the same as we did before. But now the diatomic molecule is a two-state system. So we have here the two-state involved, and we have here the dipole moment coupling with the electric field. And we also search in the literature for S-wave scattering length and P-wave scattering length that we also managed to find. And this is how the molecule look like. This is a comparison when we include only the charge dipole interaction, or if we include in addition this S and P wave scattering length. And as you see, the difference is significantly. What we see here is that the P wave, there's a resonance here, and that's what we see here. That's the resonance at short distance. But the important part, this is what the experimentalists will see in their lab, their minima and their potential could be support bound state. This is when we excite to n equal 15. Oh, sorry, there's something here. And I don't understand it, Gaspar. Let's see. Yeah, that's okay. So what we see here, depending if we go to n, like 15F or 15G, both we have enough bound state. And in each one of the potential, the dipole moment of NO, it's pointed away. The core will be somewhere here. The NO core will be somewhere here. And the dipole moment of the NO ground state molecule will be pointed in the other direction. And here you see like what is the vibrational splitting for this bound state. Here is the rotational splitting, it's around 1 megahertz. The dipole moment is very large because we have a lot of variation of these electronic states. It's around 0.5 kilo-Debye. And the Rabi frequency we also computed to create these molecules is between 1 and 10 megahertz. We wanted to n larger, and we wanted to n larger because the lifetime of this molecule is a little bit increased for n equal for larger n. And then here you see where this is n equal 40F with the even and the odd state, and that will be here the M 40G, that will be here, and there are more states. And these flat potential that they look very flat here, they support bound state. I mean, there are not many, but here you have two bound state that could be observed experimentally. And in that part of the potential, in both cases, here we have larger. There are a few more bound states. In both cases, the dipole moment is pointed away from the diatomic, like the core. But if we go to this curve over here, what we have here is that, again, they're bound state. And now what is interesting is depending in which minimum we look, as we get closer to the core, the dipole moment of the NO change direction. And you see here also that there are several, I mean, the vibrational splitting is large, the rotational excitation is also large. They have huge dipole moment, which could be controlled and manipulated with a very weak electric field. And we also have a decent Rabi frequency for the experimentalists to create it. And so we have, they could be created experimentally. So we have a proposal here how they could be created in the lab. So that will be create a sample of NO they have already, and they are working on the excitation of NO. I think they have it already. And this is how they path. They have this 2-photon transition. That's one of the example, actually. There was another example here that didn't came on the PDF file. There was one of the examples where they will start in the ground state and then go to this intermediate electronic state to end up in this excited state. And then with this excitation, they will be able to create the molecule and then resolve them experimentally. So to conclude, because I think this is already flashing in red, to conclude, I have talked about two different kind of Rydberg molecule. The one that they are combine a diatomic molecule with a Rydberg atom. We are working right now with Franck-Condon in Harvard and Simon Cornish to create them experimentally, and we are doing the calculation for them. The difference between Franck-Condon and Simon Cornish is that they are working different species. At the end, I think Simon, I made a mistake here. Simon is going to excite rubidium because it's easier for them than cesium, or they have the expertise also from Charles Adam to do it. And we are working now with Hara Kluber in the group of Tillman-Fau, and they will create these negative molecules. With that one, I would like to conclude, tempting you to go overseas and come to the cadmium workshop that I am organizing with Jim Seifer and Luis Marcasa. It's a cold atom molecule interaction. We are still open for submission if you want to present a poster, and it's going to be held in the Perimeter Institute in Waterloo in mid of July. With that one, I thank you for your attention.
Thank you, Rosario. We have time for questions.
Olivia, please be the first one.
Two brief questions. At some the first part, you were saying that you were looking if this mechanism is general. Why it should not be general? I mean, at least for this class of atom molecules.
No, it is general. Yeah. The point is, due to the Rydberg structure of the diatomic molecule, it could be, and the diatomic molecule, I mean the rotational constant of the diatomic molecule, it could be that when because what we do is to excite the rotational molecule, it could be that the rotational excitation miss this part of the spectrum. So it's general is where do I find it?
Yeah.
It's more where to find it actually.
And maybe a short second question for NO. Would you expect, because you always identify the Rydberg state of NO with the N principal quantum number, but then it is now the core which has the possibility to have rotational angular momentum. So I was wondering if you expect to have, if the NO plus is in, say, J equal 1 or 2, whatever, if it
the ground state NO?
Or even the Rydberg state, because you have the Rydberg state of NO, but then the rotation is carried by the core, by the ionic core, right, the NO plus. And so my question is that if you create NO from J equals 0, I suspect that the Rydberg state will still be in J equals 0. Not sure, but maybe. But my point is that I was wondering if then the rotational angular momentum of the NO plus, which is carrying the Rydberg electron, could play a role in all that picture or not, if you thought about that.
It's a very interesting question. We didn't thought about that, but we were considering always that the Rydberg electron is really localized in one of these orbitals, so they didn't carry out. But we will consider that. It's a very interesting question, actually.
Yeah,
we will
thanks.
So I was kind of surprised not to see a rotational projection quantum, a magnetic quantum number in the states.
No,
that you
this is not. It's the rotational.
So you always gave n, but we have an axis, and I would always suspect that the axis we should how the molecule relates to that axis should be important.
What I'm doing it's like what I am identifying there that's probably I didn't say it properly. I'm identifying like the diatomic molecule is rotating freely. What I'm fixing is this internuclear axis always. And this n is how many partial waves contribute to the basis state expansion in order to understand what do I mix there? How do I mix there?
The molecule itself, the small molecule itself, is not oriented.
It's rotating. It's oriented and rotating due to the fact of this electric field induced by the core and the Rydberg electron. And that's what is showing this partial wave, Johannes. The fact that I am not keeping in one partial wave, it's showing that the molecule, it will be oriented, either away or towards the core.
But then shouldn't be the magnetic quantum number?
It's not the magnetic quantum number, it's the rotational quantum number of the diatomic molecule.
Yeah,
and is this here from the rotational,
Yeah, exactly. So I would have expected that there's some NZ or something like this. Yeah. But okay.
So
the
projection of the total angular momentum is conserved because this is so like what I do is I couple this angular momentum to this angular of the Rydberg electron angular momentum, and the total angular momentum I work in the projection mg equal to 0. Because it's the full system is isolated, so the projection is conserved. And then I work with mg equal to 0.
Okay, I guess that was my question. Thanks.
There's somewhere. I'm sorry.
Yeah, Rosario, thanks for the great results. So there are actually two connected questions. So when you discuss the experiments that Simon is planning, then you described that these two traps will be merged. And then you talked about that it adiabatically follows your curves. I'm not sure that I fully understood this.
This is a way we describe it because I think they will make photo association.
Okay.
But what I thought, that's what we have this curve. I thought, okay, if they are close and they are some kind of movement and they approach each other, they will end in this entrance channel. They will find this avoided crossing, and then we were trying to see how is this avoided crosses cross. Okay. And that's where we include this velocity. And actually, the velocity was there, but I think in the PDF transformation it didn't come. So the velocity, the smallest one that I consider, Johannes, was like 200 centimeters per second, which is very high for this cold temperature. And that's what I said. They come so fast that the probability of crossing it's diabatically, so it will enter directly. If you want to be adiabatically, they will have to, that will be very slow, and then they will go. So at the ultra-cold regime, they will not kind of cross diabatically, but they will roll down the curve.
Okay. Yeah, the connected question is about NO. So I'm not sure if you're aware of the experiments of Ed Grant in Vancouver with these plasma, and where he sees this arrested relaxation, that the plasma stays in what could be highly excited Rydberg states for a longer time than expected. So did you consider if this kind of binding that you study there could play a role in that dynamics?
No, we didn't. We should consider.
Yeah.
Thank you for the suggestion.
So maybe in the interest of time, we'll move on. Thank you very much, Rosario.
Thank you.
Again.